Okay, the question states, two cars are traveling along a straight line in the same direction. The lead car at 24 meters per second and the other car at 29.4 meters per second. At the moment, the cars are 38.7 meters apart. The lead driver applies the brakes, causing the cars to have an acceleration of negative 1.97 meters per second squared. Okay, so there's four parts to this question. For part A, it asks how long it takes the lead car to stop. For part B, it asks what is the distance the lead car travels during this time. For part C, it asks what must the chasing car's minimum negative acceleration be so it does not hit the lead car. And then part D asks how long it takes the chasing car to stop. Okay, let's start off with a picture. So here is the chasing car, car 2. It is going at 29.4 meters per second. And then this right here is the distance, which is 38.7 meters. And then here is the leading car, car 1, and it is going at 24.4 meters per second. Okay, now let's go to a table. So for this table, we're just going to give our given information from what we just got from the information. So for car 1, the velocity, which I just said in the last one, was 24.4 meters per second. And then its final velocity was 0 meters per second. And then for car 2, the chasing car, it was given that it was 29.4 meters per second. And then also its final velocity would be 0 meters per second for both cars because they're coming to a complete stop. And then for acceleration, it was given that the acceleration of the leading car was negative 1.97 meters per second squared. And this would remain constant because this is a constant acceleration problem. And then for car 2, we do not know the acceleration yet. And then for both cars, it would start off for time at 0 seconds. But for each car, we do not know its end time. We also do not know how far each car travels until it comes to a complete stop. Okay, going into part A, we use the kinematic equation VF equals VO plus AT. So, since we already found in the table that VF was 0, we can just cancel it out here. So, we plug in 24.4 plus negative 1.97 times T. So, we subtract 24.4 on both sides, and then we divide that by negative 1.97, and then we solve for T. T here would be 12.4 seconds. Okay, going into part B, we would use the kinematic equation XF is equal to XO plus VOT plus 1/2 AT squared. Okay, to make it easier, we would subtract XO on both sides, so we would get delta X is equal to VOT plus 1/2 AT squared. So, to find delta X, we plug in our VO for the leading car, which was 24.4 meters per second. Then we add what we just got, the time, which was 12.4 seconds, plus 1/2 times our acceleration, which would be negative 1.97, times also, again, the time squared, 12.4 squared. Then, for part B, it's asking the distance, which would be delta X, so we would just solve there, and for delta X, we would get 151.1 meters. Okay, for part C. Part C is asking for the chasing car's minimum negative acceleration so that it does not hit the lead car. So, from this given information, we would use the kinematic equation. Delta X is equal to VOT plus 1/2 AT squared. And then we would plug in what we just got from part B, 151.1 meters, is equal to car 2, the chasing car's velocity, 29.4. Also that with the time, so that it would not hit the car, which would be 12.4 plus 1/2 the acceleration, which we do not know what that is, what we're trying to solve, while also doing 12.4 squared. So now we would just solve for A, and for A we would get A is equal to negative 2.28 meters per second squared. Alright, last part, part D. Part D is asking for how long it takes the chasing car to stop. So, the kinematic equation we would use is VF is equal to VO plus AT. So, also again, VF would be 0 since it's coming to a complete stop, so its velocity would be 0. So also, next thing, its initial velocity would be 29.4 meters per second. That plus its new acceleration that we just found, negative 2.28 meters per second squared times time. So to solve it, we would do minus 29.4 on both sides. So we would have negative 29.4 is equal to negative 2.28 times t. So divide 2.28 on both sides, and our answer that we would get is t is equal to 12.89 seconds. Okay, last part, the checking part. So in order to check, why don't we just plug in what we just got for our given values to see if it is equal to let's plug in our values we just got, that we just calculated, to see if it will equal our given values. So first, let's plug in our time for part A to see if it will equal VF, which would be given, which is 0. Okay, so let's do VF is equal to 24.4, and that plus negative 1.97, that times 12.4. And if you plug this into a calculator, you would find that VF would actually equal 0. So we did find that this is actually true. Okay, next part, for part C. So actually, let's do part D to check. So we would also do the same kinematic equation. VF is equal to, 29.4 plus negative 2.28 times 12.89. So now we would do this again. We would plug it into a calculator, and what we would find, VF again would equal 0 meters per second. So in turn, both of these are correct. And then lastly, for part B, we need to check if 151.1 meters is correct. So we would plug in, this is the second kinematic equation, VF squared is equal to VO squared plus 2A delta X. So plugging everything in, it would be 24.4 meters per second squared, or no, not meters per second squared, but 24.4 squared plus 2A, which would be 2 times negative 1.97, and then that lastly, that times what we got for X, 151.1 meters. And if we did calculate this and do the square root of all of these, then we would get that VF would indeed equal 0. So part B is also correct. So we found every answer from A to D for the chasing cars problem. Thank you.